There is something hiding in the laws of physics that feels almost like a quiet contradiction, an object that must exist if our equations are right, and yet has never once been seen. Not in distant galaxies, not in gravitational wave data, not in any corner of the observable universe. It's as if reality itself is refusing to cooperate with its own mathematics. And that object is the exact opposite of a black hole. You already know what a black hole is. A region where gravity is so intense that nothing escapes. Matter falls in, light falls in, and beyond a certain boundary, the event horizon, there is no return. But now imagine flipping that idea completely. Imagine a place where nothing can enter, where everything only comes out. Matter, light, energy, all expelled outward, never able to fall back in. A region not of ending, but of pure emergence. That object has a name, a white hole. And here's where things get strange. White holes aren't science fiction. They are not speculative guesses or fringe ideas. They fall directly out of the same equations that predict black holes, equations that have been tested, confirmed, and trusted with extraordinary precision. The math doesn't hesitate. It allows them just as naturally as it allows black holes. And yet, while black holes are everywhere, white holes are nowhere. This isn't just a missing object. It's a deep inconsistency between what the universe allows and what it chooses. And understanding why takes us straight into one of the most profound questions in physics. Why does time move forward? To get there, we need to carefully build the picture from the ground up. A black hole begins with collapse. Take a massive amount of matter like a dying star and let gravity do its work. As the star collapses inward, it bends the fabric of space-time more and more severely. At a certain point, that bending becomes so extreme that a boundary forms, the event horizon. Inside this boundary, the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing inside can ever get out. But this isn't just about being trapped in space, it's something deeper. Inside a black hole, all possible futures lead inward. Every path you could take, every movement through space-time that points toward the future pulls you closer to the center. The singularity isn't just a place you might reach. It's a moment you are guaranteed to encounter just as surely as the next second in your life. In that sense, a black hole takes the idea of irreversibility, the fact that time only moves forward, and embeds it directly into the structure of reality. Inside it, moving forward in time is moving toward the singularity. You cannot go back. You cannot escape. The geometry of space-time itself enforces it. Now comes the critical step. In physics, there's a mathematical operation called time reversal. It does exactly what it sounds like. It flips the direction of time in the equations. Replace time with its negative and see what happens. And here's the surprising part. Most of the fundamental laws of physics don't care. Whether it's quantum mechanics or general relativity, the equations work just as well forward as they do backward. For every allowed process, there exists a perfectly valid reverse version. So, what happens when you apply time reversal to a black hole? You get a white hole. Instead of something forming from collapse, you get something that begins as a singularity and expands outward. Instead of matter falling in, matter is pushed out. Instead of a boundary that traps, you get a boundary that repels. It's the same structure, but with time running in reverse. And mathematically, it's flawless. But reality doesn't follow. We see black holes constantly, at the centers of galaxies, in the aftermath of stellar collapse, in the ripples of space-time detected as gravitational waves. We've even imaged their shadows. They are no longer theoretical, they are observed, measured, undeniable. White holes, on the other hand, have never appeared, not once. So the question becomes unavoidable. If the laws of physics allow both, why does the universe only choose one? And the answer isn't hidden in the equations themselves. It lies in something deeper, something more subtle, something that governs not just physics, but the direction of existence itself. It lies in the arrow of time. And in the next part, we're going to uncover exactly what that means and why it may be the reason white holes don't just fail to appear, but are fundamentally prevented from ever existing at all. If this idea is already shifting how you see reality, stay with me because what comes next will take it even further. If white holes are mathematically just as valid as black holes, then something outside the equations must be deciding which one actually appears in our universe. And that something is not obscure or hidden, it's a principle you've encountered before, one that quietly governs everything from melting ice to aging, from broken glass to the flow of time itself. It's called entropy. To understand why white holes don't exist, we need to understand what entropy really means, not as a vague idea of disorder, but as a precise statistical fact about how the universe evolves. In any isolated system, entropy tends to increase over time. That's the second law of thermodynamics. And unlike many laws in physics, this one has a direction built into it. It tells you which way time flows. Why does entropy increase? Because there are simply far more ways for a system to be disordered than ordered. If you leave things to evolve naturally, they will almost always move toward the more probable state, the one with higher entropy. It's not impossible for entropy to decrease. It's just so overwhelmingly unlikely that for any system as large as the universe, it effectively never happens. Now bring this back to black holes. When a star collapses into a black hole, something remarkable happens. All the complex structure of that star, the detailed arrangement of its matter, is lost in a very specific sense. What remains is a simple object defined by just a few properties: mass, charge, and spin. All the fine-grained information about the star's internal structure is smeared out, encoded in a highly mixed, high-entropy state associated with the event horizon. In thermodynamic terms, a black hole represents an extreme. It is one of the highest entropy states possible for a given amount of matter. The process of forming a black hole from an organized star to this maximally mixed state is a clear move toward higher entropy. It follows the natural direction of time. Now reverse that process. A white hole would start in this high entropy state and evolve into something more ordered, expelling matter in a structured way, reconstructing complexity from chaos. That's not just unusual. It's an entropy decrease. It's the thermodynamic equivalent of a shattered glass leaping off the floor and reassembling itself perfectly, or a scrambled egg unmixing into yolk and white. And here's the key. The fundamental laws of physics don't forbid those processes. On the microscopic level, they're allowed. But on the macroscopic level, the level we live in, they are so statistically improbable that they never occur. That's why white holes don't show up. Not because the equations reject them, but because the universe overwhelmingly favors processes that increase entropy. The number of possible microscopic configurations that correspond to a high entropy state is vastly larger than those that correspond to a low entropy one. So when the universe evolves, it almost always moves in that direction. White holes would require the opposite. They would require the universe to choose an extraordinarily unlikely path, one where entropy decreases in a coordinated, large-scale way, and that simply doesn't happen. So the absence of white holes is not a failure of physics, it's a confirmation of it. It tells us that while the laws are symmetric, the history of the universe is not. And that brings us to something even deeper. The second law of thermodynamics doesn't just explain why white holes are absent, it explains why time has a direction at all. Because if entropy can only increase, then time can only move forward from lower entropy to higher entropy. But that raises a more fundamental question. Why did the universe start in a low entropy state in the first place? Because everything depends on that. If the universe had begun in a state of high entropy, if it had started in complete disorder, then there would be no preferred direction of time. Processes could run forward or backward with equal likelihood. Black holes and white holes would be equally common. The universe would look completely different. But that's not what happened. Instead, the universe began in an extraordinarily ordered state. The early cosmos, despite its immense energy and density, had remarkably low entropy. That initial condition is what set everything else in motion. It's what created the arrow of time. It's what made entropy increase possible and inevitable. And once that arrow was established, it broke the symmetry. The equations may allow both directions, but the universe chose one, and from that choice, everything follows. Black holes become natural. White holes become forbidden, not by law, but by overwhelming probability. So when we ask why we don't see white holes, we're really asking a much deeper question. Why did the universe begin in such a special low-entropy state? And that question doesn't just belong to physics. It sits at the boundary between cosmology, philosophy, and something more personal. Because the same arrow of time that shapes galaxies also shapes your life. The past is fixed, the future is open, and just like the universe, you are moving in one direction only toward increasing entropy, toward moments that have not yet happened, while everything behind you becomes irreversible. In the next part, we're going to step beyond the equations and into something more human, because this isn't just a story about black holes and white holes. It's a story about why the past can't be changed, why some things can never be undone, and what that means for the way you live, the time you still have. And once you see that connection clearly, it's hard to ever think about time the same way again. Once you truly understand what entropy means, the conversation shifts. This is no longer just about distant cosmic objects or abstract equations. It becomes something much closer, something uncomfortably personal. Because the same principle that prevents white holes from existing is the same principle that shapes every moment of your life. The arrow of time is not just a feature of the universe, it's the structure of your experience. Everything moves forward, not by choice, not by preference, but by necessity. The entropy increases, and with it the past becomes fixed. What has happened is locked into the history of the universe, encoded in ways that cannot be undone. And the idea that it could somehow reverse, that events could flow backward, restoring what was lost, is exactly what a white hole represents. But just like in physics, that reversal doesn't happen. Think about what a white hole would mean in human terms. It would mean that the moments you missed could return, that conversations you never had could somehow take place after the fact, that the times you were distracted, absent, or elsewhere in your mind could be replayed this time with full attention, with clarity, with presence. It would mean that entropy could decrease in very specific ways, that what was broken could be restored, that what slipped past you unnoticed could be reclaimed. And just like in thermodynamics, it's not that this is logically impossible. It's that it is so overwhelmingly improbable that for all practical purposes, it never happens. The past does not run backward. The things that were not said remain unsaid. The opportunities that passed remain in the past. The people who didn't receive your full presence at a given moment didn't receive it. There is no mechanism, no physical process, no hidden loophole that allows you to re-enter those moments and change them. The event horizon of the past is real. You can approach it in your mind. You can analyze it, reflect on it, even regret it. You can replay scenarios, imagine alternative outcomes, construct entire versions of reality where things unfolded differently. But you cannot cross that boundary in reverse. You cannot go back. And this is where the analogy becomes exact. In the same way that nothing escapes a black hole once it crosses the event horizon, nothing escapes the past once it becomes fixed. It is thermodynamically sealed. The entropy has increased. The configuration is set. The white hole, the reverse process, is not available. There's a tendency to resist this, to wish, even quietly, that the laws were different. That maybe, in some corner of reality, there exists a way to undo specific things. Not everything, just the important parts. Just the moments where, with the clarity you have now, you can see exactly what should have happened. Maybe you've felt that. The sense that if you could go back, not indefinitely, but precisely, you would act differently. You would be more present. You would say what needed to be said. You would notice what you failed to notice. That desire is deeply human. But the second law of thermodynamics does not bend to it. The entropy has already increased. The state of the universe now includes those past moments exactly as they occurred. And the probability of them spontaneously rearranging into a different configuration, a better one, a more complete one, is effectively zero. So, what do you do with that? Because the answer is not to ignore it, and it's not to soften it. The physics is clear, the irreversibility is real. And pretending otherwise doesn't help, it only delays the moment when you confront what that actually means. The only direction available is forward. And that might sound obvious, but it's more than just a statement about time. It's a statement about responsibility. Because while the past is fixed, the future is not. The entropy that will exist tomorrow hasn't yet been created. The moments that will define it haven't yet been lived. Right now, there are still conversations that can happen. There are still people you can fully meet. There are still moments that can be experienced with attention instead of distraction, with presence instead of absence. And that's the part that often gets overlooked. We spend so much time thinking about what cannot be changed that we lose clarity about what still can be. But the physics points in a very specific direction, not backward, not into hypothetical reversals, but forward into the only region where change is still possible. The future is where entropy hasn't yet taken its final form. That's where the choices still matter. That's where presence still makes a difference. And once you really understand that, once you stop expecting the white hole to exist, you start to see the forward direction differently. Not as something inevitable and automatic, but as something that still contains open space. Space where your attention, your decisions, and your actions actually shape what happens. In the next part, we're going to return to the physics, but from a different angle. We'll look at one of the most elegant tools in theoretical physics, something that reveals how black holes and white holes are connected at a deeper level, and what that connection tells us about reality itself. Because it turns out, the story isn't just about why white holes don't exist, it's about how they almost do, in a way that changes how we understand the universe entirely. And once you see that structure clearly, the boundary between what's possible and what's real becomes even more fascinating. To really see how deep this idea goes, we need to shift perspective, not just conceptually, but visually. There is a tool in theoretical physics that allows us to compress the entire history of a spacetime into a single finite diagram. A way of seeing infinity on a page while preserving what actually matters. Cause and effect, what can influence what and what can never be reached. It's called a Penrose diagram. At first glance, it looks simple, but it encodes something profound. In this diagram, time and space are arranged so that every possible path through the universe can be drawn, and the rules are clear. Light always travels at a 4-5-degree angle. Anything moving slower than light, anything with mass must follow a path steeper than that. And anything flatter than that angle represents something unreachable, something causally disconnected. What this gives us is not just a picture, but a complete map of possibility. Now, apply this to a black hole. When you draw the full Penrose diagram of an idealized black hole, what physicists call the maximally extended solution, you don't just get one region, you get four. There is the region we are familiar with, the exterior, where observers like us exist, watching from a safe distance. Then there is the black hole interior, the region you enter once you cross the event horizon. Inside that region, every future path leads to the singularity. There is no escape, no alternative route. But that's not all. The diagram also includes a region that sits in the past relative to the black hole interior, a region from which matter and light can emerge outward, but into which nothing from the outside can enter. This is the white hole region. And then there is a fourth region, a kind of mirror universe, another exterior region connected through what's known as an Einstein-Rosen bridge, often described as a wormhole. All four regions exist simultaneously in the mathematics. They are not separate ideas. They are different parts of a single, unified spacetime solution. And this is where things become deeply interesting. The white hole is not some entirely different object. It is the same geometry as the black hole, viewed from the opposite direction in time. The singularity that lies in the future of a black hole lies in the past of a white hole. They are two sides of the same structure. In other words, the equations don't distinguish between them. They describe a single object that contains both behaviors collapse and expulsion depending on how you move through time. So the question shifts again. If the full mathematical solution includes both black holes and white holes as equally real regions of spacetime, why does our universe only realize one half of that solution? Why do we live in a universe where the black hole region exists physically, but the white hole region does not? The answer, once again, is not in the equations. It's in the initial conditions. The universe we observe is not the entire mathematical solution. It is a specific slice of it, a particular realization shaped by how the universe began. The equations provide all possible structures, but the actual universe selects only some of them. And that selection is not symmetric. Because the universe began in a low entropy state, the arrow of time points in one direction. That direction aligns with the formation of black holes, not white holes. So even though the white hole region exists mathematically, it has no physical realization in our cosmos. It's there in theory, but absent in reality. And there's something quietly profound about that. The mathematics contains more than what actually exists. The full solution is richer, more complete, more symmetrical than the universe we experience. But reality is not obligated to realize every possibility. It follows a path, a single trajectory through a much larger space of what could have been. And that idea extends far beyond physics. Because the same is true of your life. At any given moment, there are countless possible paths you could take. The full solution of your life, the complete set of everything that could happen is vast. But what actually unfolds is just one path through that space. One sequence of choices, conditions, and events. And once a path is taken, it becomes fixed. The alternatives don't disappear in a mathematical sense. They remain possible in theory, but they are no longer part of your actual history. They are the white holes of your life. The unrealized reversals, the paths where entropy would have decreased, where outcomes would have been different. They exist in possibility, but not in reality. And just like in physics, the difference between possibility and reality is not random. It is shaped by the direction of time, by the accumulation of entropy, by the irreversible sequence of events that defines your experience. The past is not the full solution. It is the path that was actually taken. And understanding that clearly changes how you relate to it. Because it removes the illusion that the past could somehow be different. It replaces that illusion with something more grounded, more honest. The recognition that what happened is part of a trajectory that cannot be undone, only understood. And that understanding matters not because it changes the past, but because it changes how you move forward. Because forward is still open. The Penrose diagram shows you something else, something just as important. While certain regions are sealed off, others remain accessible. There are still paths that can be taken, still directions that lead somewhere new. And that's where the focus shifts next. Because so far, we've been looking at why white holes don't exist, why the past can't reverse, why the universe follows one direction instead of another. But there's another side to this story, one that isn't about limitation, but about what still remains possible. In the next part, we're going to explore that forward direction more deeply through the lens of black hole evaporation, quantum physics, and a surprising idea about information that changes how we think about what is truly lost. Because even in a universe where nothing runs backward, something unexpected still happens. And it might change how you see both the past and the future. Up to this point, everything we've explored seems to point in one direction. Forward, irreversible, fixed. Black holes swallow information. The past locks into place. Entropy increases, and the idea of reversing it, of recovering what was lost, feels not just unlikely but impossible. But when you bring quantum physics into the picture, something unexpected begins to emerge. Because black holes don't last forever. In the classical picture, a black hole is permanent. It forms, it traps, and it remains. But when quantum mechanics is applied to space-time, when you look closely at what happens near the event horizon, a new process appears. Black holes begin to emit radiation. Not matter escaping from inside, but energy generated by quantum effects at the boundary itself. This is known as Hawking radiation. Over time, this radiation carries energy away from the black hole. Slowly, almost imperceptibly at first, the black hole begins to lose mass. For large black holes, this process takes an unimaginably long time, far longer than the current age of the universe. But the direction is clear. The black hole shrinks. And eventually, if you wait long enough, it disappears completely. Now this raises a question that cuts straight to the core of physics. What happens to the information that fell into the black hole? Everything that ever crossed the event horizon, the matter, the energy, the detailed structure of whatever went in, seems, at first glance, to be gone forever. But that would violate one of the deepest principles in quantum mechanics, that information is conserved. The universe, at its most fundamental level, does not erase information. So which is it? Does the black hole destroy information, or does it preserve it? This is the black hole information paradox, one of the most important problems in modern physics. And after decades of debate, the prevailing view is that information is not lost. Instead, it is encoded subtly, indirectly in the radiation the black hole emits over its lifetime.